Hi everybody, this is a equilibrium law calculation video. We're going to go through the various examples of equilibrium law calculations from our booklet, and we'll see how that goes. So if you caught the live stream, you'll know that we've gone through some of this already, but we're talking about equilibrium law. This is where we take a chemical equation such as in the general form, A plus B gives us C plus D. Assuming these are all gaseous or aqueous forms, then the equilibrium law would be that there is some K value, KQ, and that would be equal to the product of the concentrations of the products raised to the power of their coefficients divided by the product of the concentrations of the reactants raised to the powers of their coefficients. So that's the equilibrium law. And using this equation, if you are given values for KQ, or if you're given values for any of the C, D, A, or B, the concentration of the reactants or products, you can work backwards or forwards to calculate the values for all the rest. And you can even do things like calculate values for chemical reactions where something has changed as well. So in our first example, you're given the equilibrium concentrations. You're asked to calculate the KQ value. This is a pretty standard calculation, and it should be a relatively quick one. Here's an example that we did in the live stream. So we're just going to move forward and do the practice. So the practice has already been worked through. Well, let's just see if we can highlight through this. If you want to see the full work through, then please feel free to go look at the live stream. So here we have set up our equilibrium law. So this was set up using the values from the equation. You can see NO2 here. NO2 has been raised to the power of its coefficient. You can see the O2 as a reactant, it goes on the bottom. You can see the NO as a reactant, goes on the bottom, also raised to their powers. Notice that oxygen is 1, so we don't write anything. Then over on the right here, we have calculated out the concentrations. So sometimes if the reactant vessel is not 1 liter, if it's say 2 liters, like in this example, then you'll have to calculate out the concentrations. And then you just punch the concentrations into your equation, replacing the appropriate values. So the NO2 had a value of 3 molar, the NO had a 1.5, the O2 had a 0.1. Push those into your calculation. Watch out with your brackets. You may have to bracket on your calculator so that the top and bottom are in separate brackets and with a division sign in between them. And then your value will be the final result here. In this example, we had only 2 significant figures at one point. Notice that here we only have 2 significant figures. So our final answer is 2 significant figures as well, if you're wondering about that. We should actually put a little decimal place here just to show that that is exact. We don't include units for these equilibrium constants. It's just not used because the equilibrium constant would have such a complicated value right now. It would have units of like, I don't know, per molarity apparently. So that would be a strange unit to use. Okay, so in type 2 questions, we have the KEQ, but one of the equilibrium concentrations is missing. So then this is a calculation that requires you to make a rearrangement to solve for the missing value. Let's do the practice question together. So here we are given an equation. Let's figure out our equation to start. So we write out our big K. We are going to put the concentrations of the products, CH4, on top, and the other products, H2S, on top, and we're going to raise that to the coefficient. We're going to put a line across for our division symbol, and we're going to put the reactants on the bottom, raised to the power of 4, and the CS2 raised to no power. It doesn't really matter what order it is on the bottom or the top, as long as it's on the bottom and as long as it's on the top. They've given you a couple of extra pieces of information. They gave you a temperature value there. That one is just there to distract you. But they did give you the equilibrium constant here. So this is our KEQ. So we're going to need that. And then they gave us some values for our concentrations. Those are already given for us as well. So, sometimes highlighting these things is helpful. In this case, you could reorganize if you wanted, or I'm going to just write it out and see what's missing. So I'm going to replace the K with the value given in the question. I'm going to replace any other values I have. So I do have a CH4 value, 0.00108 molar. And I don't have an H2S value. And this is going to be a bit of a problem later because I have that square in there. And then I have a 0.316, and that's going to be raised to a power of 4. So make sure you know how to do that on your calculator. And 0.0898, and that has no power. So now that we have the values entered into our equation, what we want to do is combine as many of the numerical values as we can. So I'm going to combine all three of these values right now. So I'm going to pull out my calculator, 0.00108. I'm going to divide that by 0.316 raised to that power of 4 multiplied by 0.0898 and close that bracket, and that's going to give me a number here, and so that's going to be 1.206, and that's multiplied by H2S, and that's still power of 2 equals 0.256. Now that there's only one number, I can move that number over to the other side by division and see what that leaves me with. So I'm going to go to 1.256 divided by 1.206. That gives me 0.212. And in this case, where I'm going to do a square root or root, I'm going to leave a couple of extra decimal places because things can get a little wonky with roots if you don't have enough significant figures. And so then we're going to take the square roots to get rid of the 2, the power of 2. And in this case, if you have a number like this and you, when I try to do the square root here, see that it doesn't let me put the number underneath. There's an alternative, is to raise it to the power of 0.5, and that gives me a value of 0.46 equals 461, I guess, if we have three significant figures, H2S. So it's a good idea to go back and do a little bit of a check here. So what I'm going to do to do the check is I'm going to calculate my value of K and see if I get close. It might not be perfect because I am dealing with some loss of significance from the imprecision of my numbers, but hopefully we'll end up pretty close. So what was that number going to be? 0.461. Bracket that up, and let's see what happens. 0.00108 times 0.461 to the power of 2 divided by 0.316 to the power of 4 times 0.0898, and that gives me 0.256. Awesome. Okay, so I mean, some of you eagle-eyed viewers out there might have noticed an edit point just before I started, just in the middle of this example. And that's because the first time I did this question on the recording, I actually went to go do the check and I got the wrong number and I had to go back and figure it out. So doing that check is super important for keeping yourself honest and, getting the correct answer. So this is our check. So I highly recommend doing a check. All right, so let's get to example number 3. So this is where things start to get tricky. So here you're given the initial concentrations and the equilibrium constant, but we don't know what the equilibrium concentrations are. So let's do this practice question. If you want to see that first question work through, then you can watch the live stream that I posted back in March. But the main concepts are going to be the ICE table, the initial change equilibrium table, where we are going to consider the initial concentrations of the starting reagents, and then we have to think about how they change with respect to their coefficients. So some of them will change only a single unit, others will change 2 units, etc., or more, and then that change can then be compared to what we think is going to be the equilibrium concentrations. Okay, so let's give this a shot. We are given a KEQ value, so let's get this K equation going because this is going to be very important. SO3, we have an NO, and that's all divided by the initial reactants, SO2 and NO2. So this is an oxygen exchange reaction, it looks like. And it says you have a KEQ of 3.5, so, a positive KEQ value. If 4 moles of SO2 and 4 moles of NO2 are placed in a 5-liter container and allowed to come to equilibrium, what is the concentration? So what we're talking about here is we are going to need a ICE table. I always write my equation at the top. SO2 plus NO2 exchanges the oxygen to make SO3 plus NO. And the initial concentration is going to be these 4 moles divided by this 5 liters. So we can do that calculation on the side here. SO3, and we can call this I, is equal to that 4.0 moles divided by the 5.0 liters. And that gives us 0.8, I think. Yeah. So you can always multiply by 2 and divide by 10. That's how I did the 0.8. So 0.8 molar. Okay. 0.80 molar. I should not have lost my 0. I know. You're all shouting at me at home. Put in your significant figures. And we are starting out with none of the original species, or none of the product species. They don't mention them, so we're going to assume they're not there. I'm going to shrink this down just to get it out of the way. All right, so the next step is how much is the container going to change? So in this case, the container is going to lose a little bit of the sulfate. It's going to lose a little bit of the nitrate. It's going to gain some amount, an equal amount of SO3 and an equal amount of NO. So remember, this is like matter that's being moved, right? We're moving matter from the left to the right. So that matter that's being moved is going to change in the ratios as the ratios predicted by the stoichiometry. And the result is going to be some new equilibrium equilibrium concentrations that satisfy this equation. So let's see what that's going to look like. So then these values become 0.80 minus x, 0.80 minus x, and then x and x. This is a really good equation. There are some equations that are going to be much harder to solve, but in general, what we try to do in this class is give you the easy ones. So I'm going to replace the k with the 3.5. Here, you know what? I'll just show you what I'm going to do by copying this, pasting that. So I'm replacing the k with the 3.5 that they gave me in the equation, and then I'm going to slowly replace these other values. So here my SO2. I have a new value here. I have 0.80 minus x. Down here I have NO2. I have 0.80 minus x. I have an NO value. It is x now. And I have an SO3, and this is also x. All right, so now that we have this equation, we're going to have to solve this algebraically. You might have some success with some math solvers, like Photomath should be able to do this, but I'll show you what the easiest way to do it is to look and realize that these are two variables that are the same being multiplied. So a better way to write this equation is to combine those underneath a square. And the same deal down here, you have two linear equations that can be replaced with a square of that linear equation. Once you have the square of a linear equation like this, then you can take the square root of the entire side and this side using equivalent actions on the left and right. We can find that square root of 3.5, which is 1.87. And then the square root on the other side is only going to cancel out these squares. And so the result is now a lot simpler. We have an x over 0.8 minus x. And we can now do some cross multiplication type action to bring things over. If you have already gotten to this point, then I'm already pretty happy. So I'm not that much of a stickler for having you work through a bunch of linear equations. I don't like this to be a math class. This is why I also support you using a Photomath type device. Or at this point, I've had a little bit of frustration with Desmos today, but let's see if we can get this to work. So if you had 1.87 and you said it was equal to x divided by 0.8 minus x, then you get a single answer, and that answer is not going to be happy. It's not giving me the answer. There was a time when this used to work. I swear. You could start moving things over, 0.8 minus x like this, and this would probably start to become clear. There we go. Okay, so that gave me the value. It does not like being in a fraction because there's some infinities there. But this is the value that we'd be looking for. So the value of x here, 0.5213. That's the value you would eventually get to if you chose to follow through on this mathematics solution. So I will continue this math solution here just to satisfy some curiosity I have. So 1.87, I'm going to multiply that by 0.8. So I get a value of 1.496 minus 1.87 x is equal to x. These ones were canceled away. And now that it's equal to x, I can put some things to the other side. I can make this 1.496 and make it equal to 2.87x. So I move this, I've moved this like that. So I got my values. And now that I have this value, I can take that 1.46 equals answer, take that and divide that by the 2.87, and there's my 0.52. So of course, an equation solver, 2.87, and that gives me the final answer, 0.521 equals x. Okay, and that is the value I did get with my Desmos, so I'm happy. I'm going to go now. This is the real trick, is that just because you got to this value, this is only the start. You must actually reintroduce this value up into your table. So I'm going to double check. I think actually I only have 2 significant figures. Yes. So I'm going to get rid of this one. That's good. That makes life a lot easier for calculating. Okay, so this x is now replaced with that 0.52, 0.52, 0.52, 0.52. And these are pluses and these are minus. So I'm minusing 0.52 here. This value is just 0.52. And you can understand why we would have to give you a whole page for these types of questions. And so our final result is going to be 0.28. 0.28 are the values. So 0.28 for our reactant, and 0.52 for our product. If you are a super studious and careful student, then of course the next thing you would do is do a double check, and we would put our 0.52, square that, divided by 0.28 squared, just as we reduced our equation down to there, and see what that gives us on that old calculator. So let's see, 0.52 squared divided by 0.28 squared, and the result is 3.44, which is pretty close. This is usually what happens when you lose a couple of values from your, you lose a couple of decimal places as you're rounding. So that's probably close enough that we can call it a day. So that's a check, and it's close enough. It looks like 0.52 was not quite right. We probably wanted to go to 0.521, and we might have had more success. So 0.521, what would that have been? That would be 0.521, and that would make this 79, and that would be, there we go. So now it's starting to round up. So this is why rounding too early is a problem. And so at some point I must have rounded too early, and my values were a little bit off. Okay. So for the fourth question, things get a little bit more wild. Here you are given the initial concentrations of some species and the equilibrium concentrations of one other species. And then you have to calculate the constant. So let's look at this question here. I actually think these are probably the easier question than the last one, because there's usually a little less resolving for x, but it can depend a little bit on the question. So here we're going to write out our equation. We've got a KQ equation. Hopefully you're really good at writing these. And this is another thing that another whole thing about it is this is really only one outcome. So if you can't do this one thing, that's not a huge deal because it's only one outcome. As long as you can you write these expressions? Can you explain the Le Chaltier principle of things that are happening? Those are bigger deals to me, or equivalent deals maybe. And I almost expect an ice table no matter what, even if it's not really that useful. I think you should do one just because it is the best way to kind of keep track of what's going on. Okay, so NO, you have 4 moles in a 2-liter container, so watch out. You've got to do a little calculation here. We've got 4.00 mole divided by 2.00 liters. So we're dealing with 3 significant figures here today. Said 3 while I was trying to write. Okay, 2.00 moles are, that's our NO2. This is introduced into a container. After a while, equilibrium is attained according to the equation blah at the equilibrium of 0.5. So I believe we are starting with 0 here. They did not indicate that there is any NO or O2. And the equilibrium is equilibrium 0.5 moles of NO is found. So watch out. They only gave you the moles, so that's moles. So we do have to divide by that 4-liter container, or a 2-liter container. So a 2-liter container, that means that we actually only have 0.250 molar NO. All right. So we know that the changes that these things must have undergone are based on the matter equation, or based on the given stoichiometry. So we would have, if we had 0 O2 and 0 NO, then the equilibrium is definitely going to be shifting backwards, because we definitely have way more NO2 than the other side. So we're kind of starting in this high position and we're going to go down, as we did in our Le Chaltier. And so we have to be shifting to the left. So we're going to be adding x to our left side, and we're going to be subtracting x from our right side in the appropriate stoichiometric ratio. If we went from 0 to 0.25, then that tells you what x is. So 0 plus 2x equals 0.250. That's the change that we observed. So then what is the value of x? Well, x must be equal to 0.125 molarities. If you need some proof of that, you can remember that you're going to divide by 2. The 0 you can ignore, and then you're going to get the x. So I'm just going to punch that in a different color. So we have 2 times 0.125. And that's the addition here. That means that for O2, we would be expecting 0.125. And here we would be subtracting 2 times 0.125. So the final values for NO2 are going to be 1.75. The final value for O2 is 0.125. And the final equilibrium value for NO was given. Punch those values into your equation. Copy. I'm going to paste that somewhere. So let's replace these values with the new values that we were just given. 1.75, or not given, we calculated them. We worked hard for those values. 0.250 and 1.25. Punch that into a calculator. 1.75 raised to the power of 2 divided by brackets 0.25 power of 2 multiplied 1.25. Oops, not 1. 0.125, 0.125. Watch out for that. And the value is that we had a syntax error because we forgot our bracket. There we go. 392, proper mathematical order here. KEQ equals 392. And so that's that one. So this one's usually a fairly straightforward, because as long as you knew the starting reagent amount, which was 0 here, and you know the equilibrium amount of one reactant, then you know how much you gained or lost of all the other ones. Okay, so given an equilibrium concentration and value of KQ, find the initial concentration. So now we're going to be working backwards, and we are going to have a couple of tricks that we're going to have to do. So here we're given the KQ value. So let me do some highlighting here. So we got the KQ value here. We have an equation. A certain amount of H2S was added and allowed to come to equilibrium. At equilibrium, this much H2 was found. How many moles of H2S were in the flask? Okay, so this could be tricky. So let's write out our equation first. So we got our K is equal to H2S squared divided by concentration of H2 raised to the power of 2 times the sulfur gas. And then we have some, let's write out our ice equation, see what kind of information we have there. So a certain amount was added to a 2-liter flask at equilibrium. So this is an unknown, right? This is a value we don't know. So I'm going to just put a big box here. That's the number we're looking for, but we do know that there was none of this stuff. So that's interesting. And then at equilibrium, so this is our ice, we know what the change would be. If we only inserted H2S, then we must be converting that H2S into the H2 and S2. So with the appropriate stoichiometric ratio. And we know the equilibrium concentration of one of those reactants. It's 0.0720 moles divided by the 2 liters. So that value is 0.0360 molarity. Okay, so we do actually know quite a bit here. The only thing we don't know is we're going to have some trouble with this number over here. Okay, so let's see what we can do. Let's go with the C value here. So we do know that if we went from 0 plus 2x and we ended at 0.0360 molarity, then x must have been equal to 0.0180. That's half of that. Divide by 2, divide by 2. We can ignore the 0. So that means that we are talking about plus 2 times 0.0180. And that means plus 0.0180. And this is minus 2 times 0.0180. And now we're going to have to give a value up here. So I'm going to put a y because I've used x already. So that I have an equilibrium value. Y is equal, or this equilibrium value is 0.0180 for the S2, and y minus 0.0360, which is this value here. That's a minus symbol there. So we do have a value now. We have something of a value for H2S, and we know we just don't know what y is. Well, this looks very familiar, hopefully. It looks a lot like any of our other solution questions because we do, in fact, also know K. We know that K is 7.5. So with all that information, we can pop all of this into this equation and then solve for this new variable y. So let's do some replacements. Here we're going to replace the H2S. I need more space, with the y minus 0.0360. We're going to replace the H2 and the S2 with the appropriate numbers. Uh, 0.0360. 180. And now we're going to do some math. Now we are going to do some math. We want to do some math. Okay, well, I guess it is a little bit later in the day here. All right, I like to combine my numbers before I move them. So I'm going to just do some math on the denominator here. So I get something like this. So now I have 7.5 is equal to y minus 0.0360 squared, and this is 2.333. Ooh, do I want to lose that? I know I had a lot of problems there earlier, so I'm going to keep that number as long as I can. Okay, I'm going to keep that answer. I'm going to bring this answer up here and multiply. So I'm going to multiply that by 7.5. So now I'm at 0.00017496 is equal to y minus 0.0360 squared. Of course, at this point, we have a square, so we should use the square root to get rid of it. So I'm going to keep that answer. I'm going to do that same trick I did earlier, just raising it to the power of 0.5 instead of a square root. And that gives me a new number, 0.013272 equals y minus 0.30360. Okay, so now I can just move that number over by adding that number to both sides. And so the result is the total number, which is 0.049227 equals y. I did have 3 significant figures, so I'm going to clean that up. Oops, I should have kept that 2. Okay. And that is my y value, so that is this number up here. This is the original value. Y equals 0.0492. And then for me, the teacher, it's going to be hard for me to find that, so this is my final number. And if you really wanted to figure out what the y value, what this total is down here, you could also take the subtraction, which actually would be this value here. So this is the value before that. So the equilibrium value is 0.0132. That would be the equilibrium value. Okay, there's probably a check here. If you used your 3 equilibrium values, you could check to make sure they came out to the K value. That would be a good check, but I think I've got a very full page here, so I'm going to keep going. Oh boy, this is the last one. I don't think I even did this question in the work. This is a very common question that we do in high school. It's one that I have some fundamental issues with. I don't really approve of it. I think it's a little bit of work for pain that doesn't actually pay off. In a world where we have equation solving devices, I don't really see the value in doing these equations, but other than from a sort of interest sake. So I think I'm going to actually put this in a separate video and about this, and just give you my word that I'm not going to ask you to do a small equilibrium constant question. So that's my gift to you. I'm going to give you a sort of a mastery problem that has these small equations and also the quadratic formula ones. I think those are just more pain than value. So I'm going to leave those. That includes this question 7 and the question 6. I think I'll put those into a separate video about sort of a mastery of equilibrium constants video, and I'll focus on that there. So with that said, this is the end of the video, and have yourselves a good day. Good luck practicing, and we'll talk to you soon.